In this lecture, we'll apply the first law of thermodynamics to ideal gases, and in particular, we'll look at the internal energy, enthalpy, and specific heats of ideal gases. In the previous lecture, we've seen that the internal energy of a pure substance in a single phase depends upon two independent state properties. For example, temperature and volume, or temperature and pressure. However, for gases at low pressures and high temperatures, the internal energy depends primarily on temperature and not much on pressure and volumes. At low pressures and high temperatures, the equation of state of the gas, that means this relationship between pressure, specific volume, and temperature. So this is called the equation of state, or more specifically, the thermal equation of state, is given by PV equals to RT. Note that the existence of thermal equation of state is given by the zeroth law, but the exact form actually depends upon the experimental data, or you can also get this equation of state from statistical mechanics calculations. In this equation, this is called the gas constant, and this is related to the universal gas constant. Let's denote it by R tilde by, so this is my universal gas constant, that is 8.314 joules per mole Kelvin. And this gas constant R over here is given by this universal gas constant over the molecular weight of that particular gas, because the units of this specific volume is meter cube per kg. So that's why we need to take this definition of the gas constant in this equation of state for an ideal gas. And any gas that obeys this equation of state is called an ideal gas, or more particularly a perfect gas or a thermally perfect gas. Now, if we have this gas that obeys this pressure, volume, and temperature relationship given by PV equals to RT, then using the second law of thermodynamics, one can formally show that this equation implies that the specific internal energy is a function of temperature only. However, to deduce this, we need to know the second law of thermodynamics. Because we have not introduced the second law of thermodynamics, we'll not go into this derivation. Instead, we'll just look at an experimental proof of why the internal energy of an ideal gas is a function of temperature. Therefore, let's look at an experiment of free expansion. So consider an experiment where we have a tank with rigid walls. Also, these walls are insulated. So we can say that these walls are adiabatic. That means they do not allow heat transfer. This rigid tank is divided into two parts using a partition, such that this partition A has the gas and this partition B is fully evacuated. And we have a thermometer dipped into this gas. Now let's say that initially this gas is in equilibrium, and then we remove this diaphragm. Then the gas completely fills this tank with rigid and insulated walls. Now in this case, because we have rigid walls, if we consider this complete system, then there's no work done on the system because there's no change in volume of the system. Moreover, there's no heat transfer to the system because we have adiabatic walls. So if we apply the first law of thermodynamics to this system, we get delta U is equal to Q plus W, but both of these terms on the right hand side are 0. That means there is no change in internal energy in this experiment of free expansion of a gas. So what this means is that if we take T and V as our state variables, then we have internal energy at, let's say, the first state before the diaphragm was removed is equal to the internal energy at the second state, and the first state is denoted by 1 and the second state is denoted by the subscript 2. However, for thermally perfect gases, it is observed in experiments that upon this free expansion of the gas, the temperature of the gas remains the same. And this is only for thermally perfect gas. This is not true for any gas. That means for a thermally perfect gas, we have U, because temperature is fixed, U, which is a function of temperature and volume in the first state, is equal to the internal energy at temperature T, which remains constant, and the volume of the whole tank, that is volume of the gas in the second state. So what this equation means is that, so here T and T are the same. So what this means is that U is not a function of volume. So what we can say is that U is a function of temperature only for a thermally perfect gas. That obeys PV equals to RT, but we've not used this relation that PV equals to RT leads us to this conclusion. For that, we'll need to use the second law of thermodynamics, but here we've just looked at an experimental proof of why gases that have ideal behavior show that internal energy is not a function of volume. So from this relation, what we can also say is that del U by del V at constant T is 0 because internal energy is not a function of volume. Now let's go back to the expression of the difference in heat capacities at constant pressure and constant volume. So let's look at the difference in the specific heat capacities at constant pressure and constant volume that we derived in the previous lecture. So this is the relation that we derived. So for a given mass of ideal gas, the internal energy is a function of temperature only, and per unit mass, the specific internal energy is also a function of temperature. That means this term over here is 0, therefore we get Cp minus Cv, that is the difference in the specific heats, is equal to P times del V by del T at constant pressure. Now we can evaluate this derivative by using this relation PV equals to RT. So V is equal to RT over P, and therefore del V by del T at constant pressure is simply R over P. So if we substitute it over here, this is what we get. So the pressure in the numerator and denominator cancel out, and what we arrive at is the difference in the specific heat capacities at constant pressure and constant volume for an ideal gas is equal to the gas constant. Note that here we have U as a function of T, and if we calculate enthalpy using U, so you have H is equal to U plus PV, and that is equal to U plus RT. So the specific enthalpy is also a function of temperature, and these functions of temperature are in general not linear functions. Therefore, if we take the derivatives, that is CV, and in this case we do not need a partial derivative because U is function of temperature only, so we can write Cv as del U by del T because U is a function of temperature only, and Cp is equal to dH by dt, and H is a function of temperature only, so we don't need to write in terms of the partial derivatives. But U and H are not linear functions of temperature, therefore Cv is also a function of temperature and Cp is also a function of temperature. They are not constants in general. This particular relation that we have derived between the difference in the heat capacities, nowhere we have assumed that the heat capacities are constants. So even if the heat capacities or the specific heat capacities are functions of temperature, for an ideal gas, the difference will always be equal to the gas constant. So Cp and Cv are in general functions of temperature, but sometimes when we do thermodynamic analysis, we only consider a small range of temperature, and over a small range of temperatures we may assume that Cp and Cv are constants. And if we make this assumption, so in addition to the assumption that the gas is a thermally perfect gas, gases for which heat capacities are constant are called calorically perfect gases. Recall that to derive this relation between the heat capacities, in the previous lecture we started with internal energy, that is a function of temperature and volume, and then here we have simplified it by taking into account that the internal energy is a function of temperature only. But if we are just looking at ideal gases, then we need not actually go through this whole complicated derivation. We can simply write, because now we can say that U is a function of temperature only. So if we apply the first law to a quasi-equilibrium process of a unit mass of gas, then, and because we are applying it for unit mass of gas, I am using a lowercase q to denote heat addition. So this is the first law, and now we can say that du is equal to Cv dt, and that's true because U is a function of temperature only, and that's a particular property of thermally perfect gases. Plus P dV is equal to dq. Therefore, dq by dt at constant pressure is equal to Cv plus P dV by dt at constant pressure, and therefore this implies that Cp, because this is Cp minus Cv, is equal to this particular term, which for ideal gases is equal to the gas constant. Now, in many engineering calculations, one needs to find enthalpy or internal energy of a thermally perfect gas at a particular temperature, knowing the tabulated values of the heat capacities or analytical approximations of the heat capacities. So for such cases, given the fact that U is a function of temperature only and specific enthalpy is also a function of temperature only, we can say that Cp is equal to dH by dt, and if you know this relation of Cp as a function of temperature, you can simply integrate from state 1 to state 2 to get the change in enthalpy. Similarly, you can write U2 minus U1, that is the difference in the specific internal energies, is equal to CVT dt integral from state 1 to state 2. And again, note that if you are given only values of Cp or Cv, let's say you know the relation for Cp as a function of temperature and you want to calculate the internal energy, then you can always use this relation Cp minus Cv equals to R, because this relation holds even if Cp and Cv are functions of temperature. Also, note that whenever you do this integration, you will always get the change in internal energy. You will not get the absolute value of internal energy or enthalpy. So you can fix one of these states and call them as reference states and then tabulate the values of internal energy and enthalpy. But whenever we apply the first law, we are only going to use the difference in the internal energy or enthalpy, and therefore whatever additive constant that you get during this integration does not matter, because it cancels out while taking the difference in the enthalpy or internal energy. We can now apply the first law to study quasi-static change in volume of an ideal gas. Quasi-static means that we go through a series of states which can be assumed to be stationary, so we can say that these states are quasi-static or quasi-equilibrium states, and such processes are also reversible processes. So if we want to apply the first law to, let's say, expansion or compression of an ideal gas, we can go, let's say, on a PV diagram. If we are at state, let's say 1, and we want to go to state 2, then there are various paths which the system can take to go from state 1 to state 2. So we'll look at two particular paths. One path is corresponding to an adiabatic process which involves no heat transfer to the system, and another process is an isothermal process where the temperature remains constant, and adiabatic process is where there is no heat transfer to the system or from the system to the surroundings. So let's look at this reversible adiabatic process first, and we'll consider that we have a unit mass of gas. Therefore, if we apply the first law, so we have the differential change in the specific internal energy is equal to dq, that is differential heat added per unit mass of the gas, minus p dv. But we have an adiabatic process, therefore dq equals to 0. This implies that du is minus p dv. Now for an ideal gas, we know that the specific internal energy is a function of temperature only, therefore du can be written as cv dt, and this is equal to minus p dv. Therefore we can write dt by dv is equal to minus p over cv. Similarly, if we start with this equation, du is equal to minus p dv, and we want to write an equation of change in temperature with pressure, then what we can do is we can invoke this relation PV equals to RT, and this relation we can differentiate, so we get PdV plus VdP is equal to RdT, and we can substitute PdV from this relation over here, and then what we will get is du is equal to RdT plus VdP, and du is equal to CVdt. There is a minus sign over here, so we have CV plus R dt is equal to VdP, and CV plus R is the specific heat capacity at constant pressure, so therefore we have dt over dP is equal to the specific volume over the specific heat capacity at constant pressure. So this is a differential equation of how temperature changes with pressure for an ideal gas whose volume changes in a quasi-static manner while having no heat transfer. We can also derive a relation between the change in pressure and change in volume. So to do that, if you look at this equation and this equation, from these two equations we can infer that dP by dV is equal to minus Cp by Cv times pressure by specific volume. So if we eliminate dt from these two equations, this is what we get. Again, note that throughout this derivation we have not assumed that Cp and Cv are constant. So in general, Cp and Cv are function of temperature for an ideal gas, and if we have a gas that is not an ideal gas, then the heat capacities will be function of temperature and volume, or temperature or pressure. So we have these three differential equations, and we can now solve these differential equations. And to solve these differential equations, we can introduce a new term, let's say gamma, that is equal to the ratio of the specific heats at constant pressure and constant volume. And because Cp and Cv are also functions of temperature, in general gamma is also a function of temperature. And we can write the heat capacities given that Cp minus Cv equals to R, and this relation also holds when the heat capacities are functions of temperature, and Cp by Cv is gamma. Therefore we get that Cv is equal to R over gamma minus 1, and Cp is equal to gamma R over gamma minus 1. So using this relation and this relation, this is how we can express the heat capacities of an ideal gas in terms of the gas constant and gamma. Now, if we make an assumption that gamma is a constant, so let's assume gamma is constant, and that would be the case when Cp and Cv are not functions of temperature, and this assumption holds for a calorically perfect gas. Now in that case, if we want to solve this equation, let's try to solve this equation. So we have dP by dV is equal to minus gamma P over V. That means dP by P plus gamma dV by V equals to 0, and this implies PV raised to power gamma is equal to a constant. So this is how pressure and volume depend on each other in a reversible adiabatic process. Similarly, we can derive relations for temperature and volume and temperature and pressure. So I can show you the derivation of the relation between temperature and volume, and I leave the relation between temperature and pressure as an exercise for you. So what you can do is, here we have pressure, so we have this differential equation in terms of temperature and volume, so we can substitute pressure using this relation for a thermally perfect gas, and then the right hand side would be equal to minus RT over CV times V, and recall that CV is the gas constant over gamma minus 1, so I can also write this as minus of gamma minus 1 into temperature over volume. Therefore, if you look at this equation, you can write this equation as dt by T plus gamma minus 1 dV by V equals to 0, and that would give us T into V raised to power gamma minus 1 is a constant during reversible compression or expansion of an ideal gas during an adiabatic process. Similarly, you can show that the temperature and pressure are related by a relation temperature times pressure raised to power minus gamma minus 1 over gamma is equal to a constant, and I'll leave this derivation as an exercise for you. So look at this relation. So if we want to plot this reversible adiabatic expansion of the gas on a PV diagram, so let's say we start from state 1, then this process would look something like this, because P is equal to some constant over V raised to power gamma, and note that gamma is equal to Cp by Cv, and this is greater than 1 for the ideal gas. Now we can calculate the work done during this expansion or compression of the gas, and the work done is simply the magnitude of that is the area under this path going from state 1 to state 2. We've already seen such a derivation previously, where we looked at the work done during a polytropic process PV raised to power n, and in that derivation we found that the work done is given by P1 V1 minus P2 V2 over 1 minus n, and in our case n is gamma. So this is the relation for work that we get, and note that P1 V1 and P2 V2 can alternatively be written as this using the thermal equation of state. So this is the work done while taking the system from state 1 to state 2, and in our notation or sign convention, W is the work done on the system. So this can also be written as, so R over gamma minus 1 is actually the specific heat capacity, so we can write this as Cv times T2 minus T1, and this is my work done during the adiabatic change in volume of the gas. And we could have derived this relation alternatively, because CvT2 minus T1 is in fact the change in internal energy of this ideal gas while going from state 1 to state 2, and U2 minus U1 is otherwise equal to work plus heat transferred to the system, but because we have this adiabatic process, therefore work is simply equal to the change in internal energy. Next, let us look at quasi-static or reversible isothermal process for an ideal gas. So for an isothermal process, pressure and volume are simply related by PV equals to RT, and that is the equation of state, but because temperature remains constant, pressure and volume are related by this relation PV equals to a constant, and we can also plot this path on this diagram. So if we start from the same state 1 as we did for the previous case, then this graph, that is P is equal to constant over volume and our state is same, would be above this blue line for the reversible adiabatic process. And why is that so? Because if we look at this, so we have dP by P plus dV by V is equal to 0 for an isothermal process. So the slope dP by dV of this curve is equal to minus P over V, and this is for an isothermal process. Whereas for a reversible adiabatic process, the slope is given by this, where Cp by Cv is gamma, and because gamma is greater than 1, this slope for the quasi-equilibrium adiabatic process is more negative. So the curve that is for an isothermal process will lie above this curve for the adiabatic process. Now we can again calculate the work done during the change in volume of this reversible isothermal process, and we have PV equals to RT, and the work done is equal to minus PdV, and P is minus RT over V. So what we get after integration is RT log V1 over V2, and this is the work done on the system to take it from state 1 to state 2. Note that if the gas expands, that is, the specific volume in state 2 is greater than the specific volume at state 1, then this quantity, this work, would be negative. That means when the gas expands, it is doing positive work on the surroundings, whereas if you want to compress the gas, that is, your V2 is less than V1, then you need to do work, positive work on the system to compress the gas. In that case, this expression W would be greater than 0. Lastly, note that during an isothermal process, you will have heat transfer of the system with the surroundings, and we can calculate the heat transfer to the system by noting that for an ideal gas, the internal energy or the specific internal energy is a function of temperature only. And note that all these relations that we have derived are for unit mass of gas. So if you were to calculate the work done to change the volume of, let's say, mass m, then this would be the work done. Now, if we know that the internal energy is a function of temperature only, then du will be 0 in an isothermal process because our temperature is constant, or delta U is equal to 0. Now, if we apply the first law to an isothermal process, then delta U is going to be 0 because U is a function of temperature only for an ideal gas. Therefore, the amount of work that is done, let's say, by the system, so minus W is work done by the system, is equal to the heat that is transferred to the system of an ideal gas, and this is heat transferred from the surroundings to an ideal gas. That means if you have this piston cylinder arrangement, where the gas is kept at a constant temperature and the gas, let's say, expands and does work on the surroundings, then that work done by the system, that is minus W, is equal to the heat that you have transferred to the system to keep the temperature constant. So this brings us to the end of our discussion on the first law applied to a control mass or a closed system. And we've seen that starting from the first law, we've then looked at that application of the first law in deriving relations between the specific heat capacities, and we have also looked at the application of the first law for control mass applied to an ideal gas. In the next few lectures, we'll now extend the first law and apply the first law of thermodynamics to control volume or open systems.